So first, I need you guys to go over your PreLab questions. Just real quickly, we're going to go through those together and make sure you guys are okay with some of the calculations. We're going to practice a little bit more with the calculations in a little bit, but I want to go through the PreLab questions. So, mostly we're going to cover PreLab question number 5. And in question number 5, they are forcing you to walk through the process of solving these problems. So first, we're going to start with the information that they tell us. And they said we're going to run an electrolytic cell at an amperage that's equal to 0.468 amps. Alright, and we're going to do it for a time that lasts for 3 minutes, which we know that this is going to end up having to be in seconds because amperage is in coulombs per second. So let's go ahead and change that to coulombs per second. And so our minutes needs to be in seconds. So 3 minutes is 1,800 seconds. All right. So the first question says, well, let's calculate the mass of the loss of the electrode. So in A, they told us we started with an electrode that had a mass of 5.1 grams, and then after the electrolysis, it was 5.073 grams, and so that gave us a mass of 0.027 grams lost. Now, why was this mass lost? Well, the reaction at this electrode was the copper solid was going to make copper 2 ions and 2 electrons. Alright, so our copper solid was disappearing and we were making copper ions. What was the evidence of that? Well, first evidence of it was that our mass was lost. The second evidence that you guys saw in your lab was that your solution started turning blue, and we know blue solutions have copper ions, therefore you know that there was some copper ions being made in this reaction. So this is going to become important later on when we get to using the mass calculation. So then they say, okay, well, let's calculate how many coulombs we have used. So we know from the equation, the only equation that's electrolytic cells, Q, which is the number of coulombs, is equal to I times T. I is amperage, T is time. So let's just plug in those numbers. So we have 0.468 coulombs per second, and we are going to multiply that by our time, which is 1,800 seconds, and seconds cancel out, and we're left in coulombs, and we grab our calculators and do the math, and we get 84.24 coulombs. Next, we're going to find out, well, how many electrons is that? And we know something called Faraday's constant, and Faraday's constant tells us that 1 mole of electrons is equal to 96500 coulombs. Well, if we were to figure out, okay, well, how many coulombs is 1 electron? 1 electron is equal to 1.602 times 10 to the negative 19 coulombs. Now, how did I get that number? Well, they gave it to you in your lab, number 1. And they also, it's just using Avogadro's number to go from moles to just individual electrons. So we're going to use this number in this step. So we're going to start with our number of coulombs. It was 84.24 coulombs. And we're going to convert that into how many electrons. And so we know there are 1.602 times 10 to the negative 19 coulombs for every 1 electron. And you grab your calculator and you do the math, and you get 5.26 times 10 to the 20 electrons were exchanged through this electrolytic cell that ran for 3 minutes at 0.468 amps. All right, next question, D. D asks us, okay, well now you know the electrons that were exchanged, how many atoms of copper were oxidized in this reaction? So we're going to start with our number of electrons that were exchanged. We know that that's how many electrons were exchanged. And from our balanced oxidation reaction up here, we know for every 1 atom of copper, we used or generated 2 electrons. So we're going to use that fact, 2 electrons for every 1 atom of copper. And do the math, and you get 2.63 times 10 to the 20 atoms of copper. All right, part E says, well, let's put together these two things. We're going to put together the atoms of copper that we just calculated that were used in our electrolytic cell. So there's the atoms of copper. And we're going to use the grams of copper that we lost, which we calculated way up in part A. So we know we used this many atoms, and that was the same as 0.27 grams of copper. And so we do the math, and that gives us 9.74 times 10 to the 21 atoms generated per gram of copper. Okay? Atoms of copper for every gram of copper. And the last step, the next step says, okay, well, we want to know Avogadro's number. Now remember, Avogadro's number is the number of atoms in a mole. And we're in grams, and we want to get that to moles. So we're going to take our 9.74 times 10 to the 21 atoms of copper per gram of copper, and we know that 1 mole of copper is 63.55 grams. Where did I get that number? Well, it's the molar mass on the periodic table. So you finish doing the math, notice that grams cancel out, and we're left with atoms per mole, which is what Avogadro's number is. So we get 6.19 times 10 to the 23 atoms of copper per mole of copper. And then the last step says, find your percent error. Well, what's our percent error? Percent error is the difference between what you calculated, 6.19 times 10 to the 23, and what it should be. And what should it be? It should be 6.022 times 10 to the 23. And it's the absolute value of the difference divided by what it should be, 6.022 times 10 to the 23, and all of that is multiplied by 100 to get a percentage, and you get 2.76% error, which tells you how far off you were from the real number. And that's not bad. So when you're doing this calculation, this step walks you through, everything in this problem walks you through how to do the calculations that you're going to have to do in your lab. Because you're going to have to calculate Avogadro's number based on your data. So make sure you pay attention to each of these steps, and now you're going to go and use your data, your amperage, and your time, and your mass lost to calculate what Avogadro's number was based on your experiment, and then compare it to what we know Avogadro's number truly is.